Okay, so we're going to take a look at one kinematics problem, a one-dimensional one. And I'm going to deal with a ball rolling across my lab table here. Now the lab table we're going to go with is, measuring it out just really quickly, looks to be about 2.5 meters. So I'm going to draw this out real quick. I've got a lab table, I've got a ball that's rolling across it, and my total distance here, my width, is 2.50 meters. Okay? I'm going to tell you that my initial velocity on my ball, it's rolling at 1.6 meters per second. Okay? And there's nothing pushing on it or anything like that. So, our acceleration in the x direction is going to be 0 meters per second squared. Okay? Because there's nothing pushing on it to make it speed up or slow down, so it's just rolling along. Alright, now I'm going to tell you that the point of this problem is to find out how long it's going to take the ball to roll from one end to the other. Okay? So, let's take a look at our usual approach to solving kinematics problems. We've drawn it out. We want to declare a coordinate system, make certain that we know where everything's going. I'm going to do our usual. To the right is our positive x. And we'll take a look at our two questions. Two questions are, what do we want? It's usually whoever's asking the question itself will tell you what they're looking for. And in this case, it's the time it takes for the ball to roll across the table. And the other question we have is, what do we have? Okay, well, going across our variables along the top here, delta x. Do we have delta x? Well, we can say that we start over here at 0 meters, and eventually we end over here at 2.50 meters. Well, that's good. Looks like we know the distances, the displacement involved. Delta, as you recall, is final minus initial. So x final minus initial. Our final is 2.50 meters, and our initial is 0. So we end up with delta x equals positive 2.50 meters. Okay, so we have our delta x. Cool. Final velocity. Well, we weren't told about a final velocity, so let's skip over that one. Let's see what else we have. We have an initial velocity. Okay, it's right here. V naught is equal to 1.6 meters per second. Now, is that positive or negative? Because velocity is a vector, we need to keep track of direction. But it's rolling to the right, and that's in the positive x direction, so it's definitely a positive. Okay? And finally, the t is what we're looking for. So I'm going to put a question mark there, and I'm going to put a star right next to it to know that that's what we're looking for. And then finally, our acceleration in the x direction, I told you, is equal to 0 meters per second squared. We'll explore later how we can determine that sort of thing. But I'll tell you now that there's nothing pushing on it or pulling on it to make it speed up. So, we have our variables. We've got an acceleration, we have an initial velocity, and we have a displacement. So, we've got 3 of our values, and we want a 4th one. Well, that's good, because each of our equations has 4 variables in it. So, we've got to find the thing that we don't have and don't want. That's our final velocity. I'll cross that guy out. So we look on our chart for the one equation that doesn't have our final velocity, which is this guy here. There's a spot right here. It looks like equation number 2 is the one we're going with. So we've got delta x equals our initial velocity times our time plus 1/2 acceleration times time squared. Okay? So our delta x, as we saw earlier, was 2.50 meters. That equals our initial velocity, which, what did I have? Our velocity is 1.6 meters per second times our time plus 1/2 0 meters per second squared time squared. Okay, well, since that's 0, the whole thing goes to 0 and makes our math much easier. We've got 2.50 meters equals 1.6 meters per second times time. So I'm going to divide both sides by 1.6 meters per second. cancels that out, we get time by itself. And time equals 2.50 divided by 1.6 equals 1.56 seconds. As we have meters per second, the meters cancel out. We have 1 over seconds in the denominator. That's what that guy is saying. Oops. That eraser is so big. So what I'm going to do to get it out of the denominator is multiply by seconds over 1. I got to do the same thing on the top and the bottom, or else I'm changing things. Seconds get canceled out, and we end up moving the seconds up into the numerator where they belong. So we end up with our time equals 1.56 seconds. Okay, so there we go. That's how long it will take the tennis ball to roll across my lab table. Now, summarizing the steps that we did, we drew out our problem so that we could see things graphically and get an idea of where our variables are coming from. We declared our coordinate system, positive x direction to the right, because that's what we're comfortable with. And so I marked my distances in there, wrote down my speeds or velocities. And then once I had my coordinate system properly determined, I could make certain that it's a velocity by having the plus or the minus as appropriate. Then I asked myself my two questions: what I want, in this case time, and what I have, and we went through and filled in what we had. And with that information, we could look through and find the equation that doesn't have whatever we don't care about in it. In this case, it was our final velocity, meaning that it was equation number 2. And then we put in our values and solved for it.